Okay. So, we have already started discussing about generation of FM, right. We have seen how to generate a narrowband FM, which is a simple way to generate, means whatever circuitry we have learned already for AM modulation, almost the same thing we can utilize. So, that was the advantage. So, at that time people were happy to use the same circuitry, and then we could see that with a kind of nonlinear devices we can actually do frequency multiplication, which was demonstrated by Armstrong, and then we could actually generate even wider band FM. Okay. So, you have to remember we will also see the other way of generating FM, but at that time historically you have to see at that time probably those circuits of direct generation of FM were not available. So, that is why probably this indirect way of generating FM was popular at that time. So, people were just trying to see if we can get an ingenious circuit which is almost derived from the amplitude modulation part. Okay. So, that was the sole reason why people started going into means narrowband FM to wider band FM. But what you should appreciate in this course, again and again I am probably exerting that all this circuitry actually comes from your mathematical understanding of the signal. Okay. That is very important, that everywhere all the circuitry you are actually doing, you are doing it from the mathematical understanding of the underground or underlying equations. Okay. So, this is something which is very important in communications any communication course, you will see that. Okay. But anyway, now let us try to see how do we in a practical circuit generate a wider band FM. Okay. So, what will happen in any wider band FM will specify something. So, last time whatever we have derived probably So, this was something we were doing. So, whenever we made a square, we could see that it is actually going up to the square of it. Okay. So, the frequency deviation becomes square. If we have a nth order this one non-linearity, then it goes up to nth order. But the problem with that is the central frequency also goes to the nth order. So, whenever we use nth order non-linearity, so basically the initial frequency deviation, suppose that was del f. So, I need a del f which is n times this. So, I get n del f, but byproduct of that is my frequency also gets shifted to n omega c. So, now we will try to see that if we target a particular frequency where we wish to put the FM and we target a different whatever I wish independent of that frequency, a deviation, how do we really make a circuitry out of that. Okay. So, that is actually means where we will be doing this FM in multiple stages, okay, or this non-linearity that we are putting, we will actually do it in multiple stages. So, let us try to appreciate that part. So, suppose we have some message signal MT, we integrate it and we pass it through that DSBSC. So, that is that narrowband FM modulator. So, this is the overall narrowband FM modulator. Okay. So, after this the narrowband FM modulator will have some specification. First of all, it will have a center frequency. So, let us say FC1, let us say that is 200 kilohertz. Okay, we are just taking one example which is also given in the book of B. Pilati. So, we are just taking that example for simplicity, and suppose that has a del f which is just 25 hertz, which is small enough, pretty small compared to that FC1, right. So, this is pretty small del f. So, basically this can be characterized as a narrowband FM, no problem in that. Suppose I want to actually generate a FM signal at frequency 91.2 megahertz. So, this is something you are used to, 91.2 FM. Okay. So, that is where I wish to put my signal, and the del f at that frequency also is specified. So, let us call that as some f c dash, okay. And there del f dash, that is also specified, that it is having 76.8 kilohertz. So, that is the frequency deviation that I want. Okay. So, this is the deviation I actually wish to have. This is actually taken from actual example. That is exactly what deviation they have at 91.2 FM. Okay. So, that is 76.8 kilohertz, overall bandwidth will be double of that, okay. Because with that frequency the actual voice bandwidth will be much smaller. So, Carson's formula you can put and it will be almost getting similar thing, around 150 kilohertz of bandwidth. Okay. So, from this del f to this, immediately what I will be trying, probably that means I need a multiplication. How much multiplication? That should be this del f divided by this del f, that I will see immediately. So, if I just do that, immediately I will get a number. But the problem is, once I get that number, if I directly apply the multiplication, this will not take it to 91.2, to some other frequency. This is where I will have problem. Okay. So, I have to do it the way it is being done in stages. Okay. So, what I will do, I will first multiply it to take it to a higher deviation and higher this one. We will of course appreciate the design of it, okay, with a simple problem. But then what I will do, because I want to now shift my carrier frequency. So, I will just do a translation, that is always easy. I take a local oscillator, from there a cosinusoidal signal, and I just get a translation with a band pass filter. Again I will be picking one of the particular frequency band where I want to put that. Okay. So, this is something I will be employing. So, I will be actually putting through a local oscillator, and then local oscillator will have its own FLO, let us say, and then whenever I multiply these two, what will happen? Wherever I have whatever that FC that center frequency will be, it will generate that FC plus FLO and that FC minus FLO. Now, I can, if I wish to have FC plus FLO, I will just filter that out and then do further multiplication. In that way, what will happen? I will have a extra variability with the local oscillator frequency, and then I will be able to probably adjust both these things, that how much stages of multiplication. So, that multiplication stage I will subdivide into two part, and then in between I will put a local oscillator which translates the frequency. So, that after doing these two multiplication along with this local oscillator facilitated translation, frequency translation, I will get exactly at this frequency. So, this is what, so general FM what they do, if this is the case, then there will be a frequency multiplier. Okay. So, this is the frequency multiplier we are talking about, that means nth order non-linearity, which translates both the things. It increases the deviation of FM as well as, so this is the indirect method. Okay. So, with that we probably create a FC2 which will be 12.8 megahertz. Okay. So, from 200 kilohertz to 12.8, accordingly you can see how much multiplication has to be given. So, this is actually multiplied into 64. So, 200 into 64 you will get this, and accordingly your del f also will be changed. So, if this was del f1, this should be del f2, which should be 25 into 64, right. So, that becomes 1.6 kilohertz. At this you give a frequency converter. So, that is the frequency converter where you actually from a local oscillator you take a signal which is 10.9 megahertz. Okay. This is whatever we are saying, that is actually being done. Okay. So, what will happen if I just do this, your this frequency, the FC2 will get translated to a higher frequency, but del f will remain the same because I am not tinkering with, I am not passing it through a local oscillator, it is just a frequency translator, it will just take it to a higher frequency, nothing else. The frequency deviation will not have any effect on that. So, what will happen? I will now go to, so this is 12.8 minus this, probably my FC2 sorry 3 should be 1.9 megahertz. Okay. So, as I have told, this might create both the frequency, this plus this and this minus this. So, here I am interested in this minus this. So, I will be putting accordingly a band pass filter which will just take out my FM signal. So, del F3 remains the same 1.6 megahertz, right. Then in the last stage I will be putting another frequency multiplier, that is multiplication with 48, and then you will see immediately you get a FM which is having FC let us say 4, that is exactly 91.2 megahertz, and the del F let us say 4, that will be exactly this 76.8 kilohertz. So, basically you have employed a multiplication of 64 into 48, but you did not do it simultaneously or together. What you did is splitted this multiplication. So, you have employed two circuit to multiply it, okay, do the frequency multiplication, and in between you have adjusted your frequency so that with the final multiplication you will get your desired FM signal. Okay. So, if you just try to do a simple problem, probably it will be more clearer. So, let us say I have a narrow band FM where the FC1, that is the initial carrier, which is 20 kilohertz, okay, and this del F1, the initial that narrow band FM initial frequency deviation, that is actually 5 hertz. Okay, so that is very small. So, it should be classified as narrow band FM, and what I want is I have a desired wideband FM where the specifications are FC4, that is 97.3 into 10 to the power 6, or I should say 97.3 megahertz FM, and del F4 is 240 probably, yes. Okay. That is 10 kilohertz, okay, or 10.24 kilohertz. So, that is the del F4 I wish. So, this is where I want to modulate, and that is the frequency deviation that I wish. And what we have also told that all the multiplier stages are actually this can all means we only have quadratic non-linearity, okay, nothing else. So, it must be 2 to the power something, we whatever we wish to realize, that should be just, it has quadratic. So, it can only make a square. So, it can generate a multiplier which is multiplication by 2. So, if I just want to have multiplication by 4, I will be putting 2 stages, but multiplication by 3, that is not realizable because I only have quadratic non-linearity. Okay. So, whatever I will have, whatever multiplication stages I will be putting, that should be 2 to the power something, nothing else can be done over here. Okay. So, that is one restriction that is coming from the circuit side, and there is another restriction that your local oscillator FLO must be within this 400 kilohertz, 500 kilohertz. Okay. That is another restriction. Okay. So, this is one restriction, and your multiplications are all, or frequency multiplier, that is actually only quadratic non-linearity is available. Okay. So, this is something you already know. Okay. So, therefore, the 2 stages we were talking about, that there will be 2 multiplication stage, in between there should be a local oscillator induced frequency translation. Okay. So, the 2 stages, with that whatever multiplication we can do, let us say in the first stage we have 2 to the power n1, and in the next stage we have 2 to the power n2. So, overall multiplication will be 2 to the power n1 into 2 to the power n2. So, this is almost like the previous one, that is actually here 64 and here 48, but 48 cannot be realized over here. So, whatever we will be putting over here, that must be realized at 2 to the power something. Okay. So, 2 stages we are putting. So, overall it should be 2 to the power n1 plus n2. Okay. So, that must be the overall multiplication factor. So, I can get a value of n1 plus n2. How do I get that? So, del f4 divided by del f1, that must be the overall multiplication, because this is the multiplication available to us. So, that should be this divided by, so that becomes 2048, okay, which is the way it is. It is 2 to the power something, it is actually 2 to the power 11, right. So, I can write this as 2 to the power 11. So, I immediately get an equation n1 plus n2 must be 11. So, this is something I know. Now, how I split, that depends on me, whether I should get 5 and 6, 6 and 5 or 4 or 4 and 7, whichever way I wish to do it, that depends on me. But there is also another thing I have to keep in mind, that my local oscillator must be restricted to this one. Whatever I keep, I will have to finally do a translation, that will be done by a local oscillator, and after doing that translation I should also match the frequency so that it goes to 97.3 from this 20 kilohertz. That is also something I will have to keep in mind. So, let us try to see what will be happening. So, let us say what is, suppose the first stage is n1 multiplication, second stage is n2 multiplication. So, then the convention I have taken in the previous example, that this becomes Fc1, then what should be my Fc2, that is this 2 to the power n1 is this 64. So, that multiplied by this one. So, if I say Fc2, that must be Fc1, which was 20 kilohertz according to our example, okay, multiplied by 2 to the power n1. So, I get a value of Fc2, right. So, this is something I have got, and correspondingly I can also write Fc4, that must be 2 to the power n2 into Fc3, right. This Fc3 is being generated due to the local oscillator, means due to the interaction of Fc2 and local oscillator, right. So, if you just try to see over here, that is the Fc1 del f, from Fc1 with multiplication I get Fc2, okay, and this Fc4 is my final target. Fc4 is generated due to this multiplication. So, 2 to the power n2 into Fc3 should be Fc4, that is what we have written. Fc4 must be 2 to the power n2 into Fc3, and Fc2 should be 2 to the power n1 this stage into Fc1, that is something we have written. So, these two equations are always valid. Now, what will happen? Once we get these two equations, now I have another relationship between Fc2 and Fc3. So, how the Fc2 and Fc3 is being generated? My Fc3 can be either Fc2 plus or minus FLO, or it can be FLO plus minus Fc3 if FLO is much bigger. Okay. So, it depends on these 4 possibilities. So, it can be also FLO plus or minus Fc2. So, I have 3 options actually. Plus will be in both cases same. So, I should write this. So, there are these 3 options which I can play with. With that the frequency should all match. So, this equation and this equation, wherever it satisfies that FLO is within 400 and 500 megahertz, as well as all n1 and n2 are integer value. If all these things are satisfiable, then only I can get a solution. So, what we will have to do is now start taking all 3 cases one by one. So, the solution I will not be doing, it is easy, you can do that. So, the solution will be just take one by one, for each case try to see if we get something meaningful. you try to calculate the FLO from this particular equation. So, suppose first case I take FC3 is equal to FC2 plus FLO, then immediately FLO will be FC3 minus FC2. Okay. So, FC3 you can represent with respect to FC4, which you know, okay, and FC2 you already know. So, once you start putting that, you will be getting a relationship for FLO. Now, FLO you put that condition, it must be 400 to 500, and then try to see whether N1 or N2 I can choose as integer. Any integer value will give me a feasible solution. If that is not the case, go for the second case, and if that is also not satisfiable, go for the third case, and you will see probably solution in one of them. Okay. So, this is how a general FM transmitter, when you try to do it in indirect method, is being generated. Okay. So, of course, you will have a unit which is called the nonlinear modulator. Okay. So, that nonlinear modulator generally people will be designing a unique one, because they do not want to design for anything customized, that you say okay I want 63 nonlinearity, that is very difficult to design. So, generally people will say okay I will just give you quadratic one, and then you want to make whatever you like. This particular practical circuitry we have seen that I will give you a quadratic one. Now, you whatever you wish to make, you take multiple such quadratic one and you just design the circuit. Okay. But you can see already there are difficulties in FM modulation. So, what is happening whenever I do that, initial modulation, that narrowband one was very easy, but after that it is just too many nonlinearity stages followed by a frequency translator, and then again followed by some more nonlinearity stages, and this nonlinearity has to be very closely monitored and controlled. Little bit of biasing factor which goes here and there, your complete nonlinearity will change, and accordingly there will be different frequency which will be generated. So, probably that was a very problematic one in FM generation. So, what we will try to see is what happens if we can try to get a FM modulator which is a little bit simpler than this. Okay. And that in that quest only people started getting the circuitry for direct modulation of FM. Okay. So, we will now try to talk about the direct modulation. Okay. So, FM direct modulation has been actually done. This is just there is only one device which can do that, that is called VCO or voltage controlled oscillator. So, this is the single device which can actually do FM modulation directly. Okay. So, we will try to just explore what this VCO is. So, basically what happens, people realize that this is a voltage controlled oscillator. That means it is actually a oscillator where you give a input voltage. Okay. So, whatever input voltage you will be giving, depending on the amplitude of that voltage, your oscillation frequency should be varying. Okay. That is why it is named as or termed as voltage controlled oscillator. Okay. So, generally a oscillator is designed by a combination of inductor and capacitor, right. So, this is something we all know. So, in any of the oscillator, either you take it Hartley or Colpite oscillator. So, our oscillation frequency is generally where L is the inductor and C is the capacitor. What people have realized over years, that if you have a semiconductor device and you reverse bias it, that is a means we know that in reverse bias it acts as a capacitor, and what people have seen also that you can actually control that capacitor with respect to the input bias voltage. So, that was the sole initiative which has started giving some hope to generate voltage controlled oscillator. So, basically what you can now do is that capacitor value can be, we are targeting this, capacitor value can be now modulated with a input signal. Okay. So, the bias you give, that reverse bias suppose semiconductor device which has a capacitor value, and that you use as part of that semiconductor capacitor that oscillator, whether it is be it Hartley or Colpit, whichever oscillator you have, you take this as a capacitor, a reverse bias semiconductor, and then the bias voltage you give to that, the capacitance value will be dependent on that. So, that is called actually varicap. Okay. So, it is known as varicap or variable capacitor. Okay. So, if we have that, so let us say we have that equation of that capacitor value is something like this C0 K mt. So, these are actually constants of that varicap. Okay. So, what happens if you give a input voltage and you will have a capacitor, that capacitance, that value will be dependent on this, and it has a linear variation over a small range. Of course, it is not for any range, any input voltage you give, it will not be following a linear relationship, but for a particular region you will be finding that it is following a linear region or linear variability. So, we will be targeting that one. Okay. So, immediately what happens to my omega 0 of that particular oscillator. So, that should be my L does not vary, but C is now actually C0 minus K mt. I can write it this way, or I can write it as I take out L C0. So, I will be having something called 1 minus K mt divided by C0 to the power half. Okay. Or I can write it as 1 by L C0 1 minus K mt divided by C0 whole to the power minus half. You know why I am writing this? Because now I will do a Taylor series expansion, that is something which I will try to do. As long as this K into mt is less than C0, this particular term will be small enough, and if I do a Taylor series expansion, what I will get? I will get the first term, then the second term is still valid because it is the linear term. After that it is just quadratic of this one, where this Kmt by C0 is much less than 1. So, I can actually neglect those terms. So, basically immediately I will get this omega 0 is equal to 1 by root LC0 1 plus Kmt divided by 2 C0, and all other terms will be neglected. So, I have just done a Taylor series expansion as long as this particular thing is valid. So, generally what will happen, this mt is it remains linear in a very small region. So, this condition is almost all the time means valid. So, if that is the case, we get a omega 0. Okay. So, I write that omega 0 as omega c into 1 plus K mt by 2 C0, where omega c is equal to 1 by root over L C0. I can write that. Okay. Or I can write this as omega c plus some Kf into mt, where Kf is just omega c into K divided by 2 C0. Fine. So, this is actually the varicap's rest capacitor, probably when mt is 0. This is the inductor value which is fixed for that particular oscillator, and these are all the parameters which are coming from the particular oscillator. So, immediately I can get some Kf of that particular oscillator and I get some omega c of that oscillator. So, this omega c is actually termed as free running frequency. Whenever mt is 0, that is the frequency with which it will be oscillating, and then depending on mt there will be a linear variation where the slope of that variation is Kf, which is also determined by the particular capacitor. So, this particular oscillator, now what is happening, his frequency is a potentially linear function of my input voltage. So, that is what I wanted to design. I wanted to design a particular oscillator whose oscillation frequency is directly dependent or linearly dependent on the input voltage. So, once this is being done, it is very easy, you will now see to generate FM. Okay. So, in the next class what we will try to explore is with this how do I generate FM, and then probably after generation we will try to appreciate how do you demodulate FM. Okay. So, that is something next we will be trying to see. Thank you.